The Appalachian Mountains are 480 million years old. They are older than the first tree, older than the first land animal. By every rule of geology, they should have eroded into a flat plain hundreds of millions of years ago. But something is pushing them up from below right now. Geologists cannot agree on what is doing it. There are at least 4 competing theories. One involves a blob of hot rock 350 kilometers wide, slowly migrating beneath New England. Another points to an ancient subducted plate sinking toward Earth's core. This is the mystery dividing geology, and it is happening beneath 200 million Americans. Stretching from Alabama to Newfoundland, the Appalachian Mountains are among the oldest ranges on Earth. Their roots reach back nearly 480 million years ago, long before the first tree or land animal ever appeared. Over this immense span of time, the Appalachians have endured 4 major collisions between ancient continents, each one squeezing, folding, and piling up rock to heights that rivaled the Himalayas. The last of these colossal collisions, known as the Alleghanian orogeny, ended about 180 million years ago. Since then, the great tectonic engines that built the range have fallen silent. By every rule in the geology playbook, a mountain belt this old should have been worn down to a broad, nearly featureless plain. The term for that is peneplain, a landscape so subdued that only faint hills and gentle river valleys remain, the ghosts of mountains long erased by erosion. This expectation is not just theoretical. Evidence from rock cooling ages, river sediments, and the volume of material shed to the Atlantic coast shows that by the time the Atlantic Ocean began to open, the Appalachians had already lost more than 1 kilometer of relief. By the late Jurassic, they were well on their way to becoming a low rolling plain. Yet when you stand on the summit of Mount Mitchell in North Carolina, you are 6,684 feet above sea level, the highest point east of the Mississippi. The Blue Ridge still rises in sharp ridges and plunging gorges. Waterfalls thunder down cliff faces. In places like the Kulisaja River Gorge, the landscape is steep and rugged, not the gentle terrain a 180 million year old range should display. It is as if the mountains have gotten a geological facelift, defying the slow, expected march toward flatness. This contradiction is at the heart of the mystery. If the last great mountain building ended nearly 180 million years ago, why do the Appalachians still stand so tall and rugged? What forces are at work beneath the surface, pushing up these ancient rocks long after tectonic collisions have ceased? Some geologists see signs of recent uplift, evidence that something is actively raising the land today. Others argue the apparent rejuvenation is an illusion, created by rivers reorganizing, climate shifts, or the quirks of erosion. The only thing everyone agrees on is the standard explanations do not fit. The Appalachian Mountains should be flat. They are not. And that simple fact demands an answer. In the Kulisaja River Basin, the Appalachian Mystery shifts from broad landscape impressions to hard measurement. Here, the evidence is not a matter of interpretation. It is inscribed in the topography itself. High-resolution LiDAR scans reveal a stair-step pattern carved into the river's profile, a series of sharp drops known as kinnick points. These are not subtle ripples. 14 distinct Nasco points line the main stem and tributaries, each marking a sudden increase in river gradient. Above these points, the land stretches out in gentler slopes, and below it plunges in steep, rugged descents. The difference is dramatic. Hills that once rolled now stand as abrupt cliffs, and valleys deepen into narrow gorges. The numbers tell an even starker story. Since the Miocene about 12 million years ago, the local relief in the Kulisaja Basin has grown by more than 150%. That means the vertical difference between the highest ridges and the lowest valleys has more than doubled in geologically recent time. LiDAR-based maps show the highest nick points, clustered between 1,250 and 1,530 meters in elevation, with a mean at 1,380 meters. Downstream of these breaks, the terrain is not only steeper but also more prone to landslides and rapid erosion. The dataset is precise. The original inventory mapped 11 nick points, and a 2025 update pushed that count to 14, confirming the trend across roughly 250 square kilometers of watershed. To pin down when this transformation began, researchers turned to cosmogenic dating, specifically measuring the concentration of beryllium-10 isotopes in bedrock exposed by river incision. Samples taken just below the nick points yield exposure ages averaging about 6 million years. This means the current landscape, with its sharp relief and plunging gorges, is far younger than the rocks themselves. Additional support comes from volcanic ash layers in the region, which date the older, gentler Miocene surface at around 15 million years old. The contrast between these two ages, an ancient subdued surface and a much younger rugged one, locks in the timing of the change. The magnitude of this shift is not a matter of debate. Multiple independent studies, using both physical mapping and isotopic clocks, converge on the same result: a basin-wide quantifiable increase in relief driven by nick point migration and rapid incision. The landscape itself has become a forensic record. Any theory about what is happening beneath the Appalachians now has to answer for these numbers. The data from the Kula-Saja Basin are not just suggestive, they are definitive. Whatever is driving the uplift-like transformation here, it is measurable, recent, and real. Beneath the northern Appalachians, seismic imaging has revealed a massive body of unusually hot rock, an anomaly stretching 350 kilometers wide and extending from about 50 to 250 kilometers below the surface. Temperatures inside this region run roughly 220 degrees Celsius hotter than the surrounding mantle. For geologists, this kind of deep heat is a game changer. Hotter, buoyant mantle can push up overlying crust, much like a hot air balloon lifting a patch of ground from below. The presence of this anomaly offers a possible explanation for why parts of the Appalachians seem to be rising again, long after tectonic collisions ended. But the story gets complicated. Not all researchers agree on how this thermal anomaly originated, or even when it began influencing the region. One camp traces its roots to the opening of the Atlantic Ocean about 180 million years ago, arguing that a surge of upwelling mantle accompanied the rifting of continents. Another group points to a later event about 80 million years ago, when Greenland and North America parted ways, suggesting the anomaly started much farther north and has since drifted nearly 1,800 kilometers to its present location. Tomography and mantle flow reconstructions support both timelines, but each predicts a different pattern and timing of uplift at the surface. Even within this single theory, the debate remains fierce. Is the heat source ancient and stationary, or is it a younger, migrating pulse that continues to reshape the land? The answer matters, because the timing and movement of this anomaly set the stage for how the mountains above respond. Some geologists argue that the rise of the central Appalachians is not just about heat from below. They point to the weight of a sunken oceanic slab, like the ancient Farallon, now buried deep beneath the crust. As this dense slab settled, it bent the crust above, flexing it upward along the edges. Flexural isostasy models built from seismic and gravity data suggest this bending could have lifted the land by 150 to 400 meters, enough to match the dramatic relief and uplift seen in places like the Kula-Saja River Basin. The numbers align with what is measured on the ground. Others see no need for a deep trigger. Landscape evolution experiments show that rivers, climate shifts, and rock type alone can reshape terrain. Simulations have recreated sharp nick points and stepped river profiles by modeling sudden sea level drops, changes in rainfall, or river capture. Even the movement of steep river sections can be explained by erosion rates or softer rock layers. Both camps find support in the data, keeping the debate alive over what truly sculpts these mountains. Deep beneath the surface, the story of the Appalachian Mountains is still unfolding. Seismic tomography has traced the path of the mantle anomaly, a mass of hot rock drifting eastward at about 20 kilometers per million years. This is not a vague estimate. By comparing time slice images from 2009, 2016, and 2023, scientists have watched the anomaly's centroid shift steadily across the subsurface, like a slow-motion pulse moving under the crust. The numbers are clear. At its current rate, this thermal body is on track to arrive beneath the New York region in roughly 15 million years. Projected maps show its trajectory, sweeping from its origins near the Labrador Sea toward the heart of the Northeast. On a human timescale, the movement is glacial, but in geologic terms, this is a sprint. The implications ripple outward: the future of the landscape, the possibility of renewed uplift, the fate of rivers and valleys, all depend on where this deep heat goes next. For the scientists tracking its path, the Appalachian Mystery is far from over. The ground beneath our feet is shifting, even if we cannot feel it yet. Beneath America's oldest peaks, the mystery endures. Is a hidden force giving the Appalachians a modern facelift, or are we fooled by surface tricks? 4 major theories, no consensus. Each new study turns up fresh evidence and fresh questions. Sometimes even the world's oldest mountains refuse to settle. Share your thoughts below.